Okay, thanks. In this week, I will give 3 lectures, and in the next week, Zhilin will give the second half, which is 5 lectures. In this week, I will give some background introduction and cover 3 topics. The first, I will recall the local L factors and the gamma factor. So this is larger enough? Okay, thank you. So in the second part, I will cover the basic functions, review the basic function. And the third topic is on the algebraic monoid. To get the partial asymptotic behavior informations of the basic functions. So this is the plan for this week. Okay, in the morning, we already have recall the local Langlands correspondence and also the L parameters. So I'm going to follow Witag's notation for the local Langlands correspondence. And we have a set of Langlands parameters. Let's say it's G. The G is still connected split reductive group defined over F. And in all my talks, I'm going to restrict to the local fields. So I take the F. Is a local field of characteristic 0. Okay. So we have the Langlands correspondence give us a surjective finite to 1 map goes to the irreducible admissible representation of G. And in the morning, we can also define the L factors on this set, and also the Epsilon factors. Sure. Let me see, surjective. So. Oh, yeah, sorry. Yeah, let me see. Right. Okay. So we have the L factors and Epsilon factors. So, sorry. Okay, so in today's lecture, I'm going to review, give the more details how do we define those local factors on this Galois set. And in the second half, we're going to discuss Braverman-Kazhdan-Ngo's principle. How do we give a integral? How do we give constructions for the representation theoretical set? This is what we're going to do for the next week. Okay. And in my talk, I'm gonna fill a lot of details regarding to these topics. It's quite easy, and even you have the jet lag, you still can get it. But I'm gonna give some homework and exercise for you for the holidays. Okay, so in order to recall these L factors and the local L factors and the Epsilon factors, I will start from the representation of the V group. Okay, I'm still using the WF to denote the V group. So let's just forget the SL2 part at this moment, just focus on the V group first. So I have a representation from goes to the complex finite dimensional representation. Is called admissible. Okay, and I'm going to recall Wittek's definition in the morning. So we need this sigma is smooth, and also the image is semi-simple. I mean, the image consists of the semi-simple elements. Okay, so this is the one of the, if we have consider the L parameters, we need to take the Weil-Deligne group, and we have the SL2 part, which is the restriction is algebraic. And now we're going to stick on the Weil group first. Okay, so let me give you examples over the Archimedean fields and the non-Archimedean field first. What are those Weil representation could be? Okay, let's see the complex case first. We know this Weil group is going to be just C cross. And in this case, the irreducible representation is going to just be the one-dimensional character. So we can parameterize by an integer and a complex number. So we can parameterize all the characters in this way. And if you apply the local Langlands correspondence in this way, this is also a character of the GL1C. So this is the easiest case. And now let's see how about the Weil group of the real. And in this case, we know that WR is the order 2 extension of the C cross. It's have two cosets. One is C, and the other one is J times C cross. So, and in this case, we could have a dimensional 2 irreducible representation. And for the characters, all the characters parameterized by a sign and also a complex number. Okay. So which means for the complex part, we take the absolute value. And for the J, it's mapped to plus or minus 1. And if we apply the local Langlands correspondence, in this case, the J is corresponding to the sign, the quadratic characters for the real number. Okay, and now let's see the two-dimensional case. Okay, for the two-dimensional case, all those irreducible representation is parameterized also by the integers and a complex number. So we have an integer which is greater or equal to 1, and a complex number. And now we're going to describe this two-dimensional representation. So let's assume this representation have a basis. And the representation acting on this basis is given by following. And also we have the J part. Okay, so those are all the irreducible representations for the weak group of real numbers. And in the general, if you have an arbitrary admissible representation, and it's not hard to see, this admissible representation is always semi-simple. So it's always going to be break down to the direct sums of these irreducible ones. And also, in the second case, this two-dimensional irreducible case, we know this is going to corresponding to the discrete series of GL2. So I just separate these two variables, two invariants. I associate T for the twist of the determinants, the character of the determinants, and this part is the discrete series arising from the SL2 case. Okay. Sigma J E1 goes to E2, E2 the J, you mean this one? yeah, it's symmetry. Thank you, sorry. Okay, so this is, all these cases give us the Archimedean case. Okay, over the non-Archimedean case, unfortunately, I cannot give you the complete list like this. So I'm going to give you some lower rank examples. So also let me give you an example about the two-dimensional irreducible representations of the weak group over the non-Archimedean case. So I'm going to stick on the periodic case with I add another constraint. Take the residue, the characteristic of the residue is odd. Okay, and now let me introduce an admissible pair to parameterize those two-dimensional irreducible representations. Okay, I'm going to take the E to be a quadratic extension over F. And the chi is going to be a character of E cross. Okay. And I don't need all the characters. I want to specify some particular characters. So I need the chi satisfies following conditions. Okay, in order to get the irreducible representation, so I need the chi does not factor through the normal map. And the second is a particular case for the level 0 case. So if I have a chi restrict to the 1 plus the uniformizer times the ring of the integers. Here the pi is uniformizer for the quadratic extension E, and the OE is referring to the ring of the integers. Okay. Okay, if we restrict to this compact subgroup is factored through this normal map, and we're going to take give the extra constraints, take the E is the unramified quadratic extension. So this is the two conditions we put on the chi. And for such a pair, the E and the chi, we're going to call this is the admissible pair. Okay, and using these admissible pairs, we can construct two-dimensional irreducible representations for the Weil group. So let's do that. Okay. And I'm going to denote the AE for the Artin's reciprocity map, and this is going to give us the GL1 local Langlands correspondence for the periodic case. And we're going to transfer from the Artin's reciprocity map to give characters over the Weil group. And this map actually is factoring through the abilizations of the Weil group. So this is going to give us an isomorphisms on the multiplicativity group. So it's going to make sense we take the inverse in this case. And then for this, it's very easy to describe the character on the field set. And now, if we compose with this inverse map, we're going to get characters on the WE. And the WE is a subgroup of the WF with index 2. So we can do the induction to construct a representation of the WF. Okay. And because the two conditions we put here, so this induced representation is going to be irreducible. Okay. And also, because the constraints we put on the characters of the residue field, and actually all the two-dimensional irreducible representation is arising in this way. So in other words, if you look at all the two-dimensional irreducible representations, admissible representations, of WF. So this set is bijective to all these admissible pairs. Okay, so this is 3 examples regarding to the Weil representation. Okay. And next, I'm going to show you how do we associate the L factor to those representations. And also in this case, if we apply the local Langlands correspondence, and this set is corresponding to all the supercuspid representations of GL2. So this is the rough idea. How do we apply the local Langlands correspondence to these 3 fields? Okay. And now the next, I'm going to move on to the local L factors. Okay. So for the local L factors, I will define the local L factors for those Weil representations first. Okay, and we know these representations are semi-simples. So if we start from 1, we always can decompose it as the direct sum. Okay, so for the epsilon factor and the L factors, the first, they satisfy the additive properties. So which means for the L factors of this direct sum of the 2 Weil representations, this is the product of the 2 L factors. And same for the epsilon factor. Okay, in the morning we already see how do we define the local L factors for the non-Archimedean over the non-Archimedean place. And now I'm going to give a full recipes for the Archimedean place. So I'm going to take the result to be as a definition to shorten my talk. And also it's going to be accessible to do the homework. So let me consider the, let me state the L factors for the real field first. Okay. And because we have these additive properties, so we only need to define for the irreducible one. And we already have the full list for the irreducible representations. So we only have 3 cases. And this is corresponding to the representation parameterized by plus and a complex number. And also we have minus t. Okay, this is for the two-dimensional irreducible representation, which is the discrete series. I mean, the essential discrete series. And this is for the real case. And now let's see the complex case. Okay, so this is the complex case. Here is the pi, the gamma is the Euro gamma function. And the pi is the pi, it's not the representation. Okay, for the Archimedes case, the epsilon factor is also very simple to write down. And here's the precise and additive characters for the real number and the complex numbers. For the first one, the psi is given by an exponential function. And the second one is over the complex number composed with the trace. Okay, so the precise additive characters or epsilon factor is also depending on this psi, and the higher measures defined over the field. And in this case, we take the Euro-Lebesgue measures. Okay, so this is what happens for the Archimedes case. And my first exercise will be compute later on. We're going to compute for an arbitrary row. We expect to we can explicitly compute the L factors for arbitrary complex representation rows. So let's move to that later. And for the non-Archimedes case, it's more complicated. And for the local L factors, we already see. Okay. So this I is also referring to the interior group, and this is we don't have the SL2 part, so I don't have the subscript n here. And this is the image of the Frobenius group inside of the GLV. This is the formula. This is for the local L factor over the periodic case. And let's see the epsilon factor. And for the epsilon factors, the definition is given by the following existence theorem. So we're going to fix a additive characters. So let's take a psi be a non-trivial additive character. And we're going to consider E is running over all the finite extensions over F. Okay, so Delay and Tate proved that there is always exists such a function which is also unique. So this function is associated to every admissible representation of the V group, and which is the polynomial of the QS and Q negative S, and also the invertible element in this polynomial ring. Okay, and our sigma is depending on, this is a complex function with the variable s, and also depending on the additive character we choose, which is also depending on the Howard errors in this case. But in our content, I just normalize the Howard error to be the one with the volume at the ring of the integer equal to 1. So I'm going to fix that Howard error. And here's the psi E, is just the psi compose the trace. And we need this family of the functions to satisfy the following three properties. So the first case is the GL1 case. Okay. And for the GL1 case, we expect this function, the epsilon factor, equal to the epsilon factor defined from the Tate thesis. This is this side is the invariant we associate to the Galois side for the V representation, and this side, the invariant is associated to the characters, so the representation theoretical side. Okay, this is the representation. The chi is the one-dimensional representation of this E cross, the GM. Okay, so this is the first property is our base case, and the second property is the additive property we just discussed. And the last part is we can allow us to do the induction. The last part is the inductive in degree 0. Okay. So in this case, we have the one is the trivial representation. Okay. The n is referring to the degree of the extension. So this is allow us to reduce to the character case. And this is part of the right-hand side is the Langlands constant. Okay. Sorry? Yeah, only depending on the other side, everything is just a trivial representation, so it's only dependent on the field extension. Thank you, yeah. Okay, and for this, using this, we can use this as a definition of the epsilon factors. So it's going to be only the unique. And also, if we fix the choice of the additive character, for example, we choose the additive character of conductor O, the conductor of the ring of the integer, and it's gonna only depending on the sigma itself. So if we do that, we're gonna have a simpler version for the epsilon factor, which can be written down as 40. Sorry? The nth power. Which the n is the degree of the E over F. Yeah. Okay, so let's see. We have the epsilon factor is equal to. So this is the monomial polynomials of the Q to the negative S. And this n sigma is an integer, which is the arcing conductor. Sorry? To be. I think, sorry, it should be the degree of, check. Yeah, I don't need this n. This. Oh, yeah. Sorry. Yeah, thank you. Yeah, you are right. I think exceed, what do you mean, Harry? I did think the 0 case, if n equal to 0, how do you define? You mean the n equal to 0? Right. Okay. Yeah. Okay. Okay, so let's see. Oh yeah, so here we have the n sigma is the Artin conductor. Okay, and in general, we also, without restrict the Howard mirror or the additive characters, so we always have the functional equations for the epsilon factor. Okay, so the sigma check is the country gradients of the sigma, and this is psi inverse. Okay. Okay, so this is just to finish the invariant associated to the weight representation part. And for the weight dealing groups, we need associated to the SL2 part. So for the SL2 part, let's see how do we give that for the, how do we define the weight dealing group, the L parameters. So we still take the G's connected split reductive group, and we take the G check is the complex dual. So in this case, we know the L group is just the split. Okay. And we consider this a simple case, and now let's see. We take the phi to be the L parameter. And the rho, I'm going to change the notation a little bit. I'm going to use rho for the complex representation of the G check, the complex dual. Okay, we use this composition. We have the phi is a map, is the L parameter for the for G. So it's a map goes to the G check, and we have the representation rho is going from G check to the GLNV. So if we compose these two, this is going to give us a new L parameters for the GL. And then we use the L parameter, we use the local L factors, the definition for this local L factors for the GL case to define this general case. And we already see this in VTEX definition. Okay. And now, because this is everything, we know it's restricted to the V part is semi-simple, and also you have the SL2 part is also algebraic. So this whole parameter is also semi-simple. So this is sigma n is referring to a dimension, an admissible dimension of the V group, and this is the n-symmetrical part for the SL2. Okay. So in the morning talks, we are referring, this is the capital N is the unipotent elements. And in here, we just give a more explicit version. So this Vn is referring to the representation associated to this sigma n. Okay. Oh, sorry, it should be this different file. Okay, and for the epsilon factors, we only need to define this local root number and plus this arting factors. We can determine this epsilon factor is in general case. So for the arting factor, and also the epsilon root number, the local root number. Okay, so in this inductive formula is also including to the L parameters for the GLN case. So if previous we only defined for the V representations, and in this case you also can think about this G is just the GLN. So this inductive formula also works. Okay. In parentheses 5, yeah. You mean this line or this line? Second line, this one?
Second last line.
Second last one, this one?
Yes.
Okay.
What is
The left-hand side is a conductor of the phi. Too many ends. Oh, yeah. Sorry. Yeah, you're right. Yeah, this n is referring to the direct sum, and this is the arting conductor. I just breaking down the row into these pieces. Yeah, I change the row, the sigma n on all the symmetrical n is going to be changed. Oh, you mean this one? Oh, yeah, of course. And yeah, I mean, this part is also not just depending on the phi, but also the row. Yeah, of course. n phi rho is same as the n phi rho is referring to the referring to this. So let me. I want to use the different letters to distinguish this n and this subscript n. So this n is just the arting. And this is the definition for this arting conductor. Okay. Yeah, this is the Frobenius. This is the phi restricted to the O n is same as sigma. So that's the decomposition. It's the sigma n if you prefer. Okay. So I'm taking to the restriction. So this is okay. For zero case, we have sorry, one of them should be 0. Yeah. This is 0. This is 0. One of them is 0. One of them is 1. So this is 0. Okay. Okay, and so this is the 4 cases for the local factors, and using these L factors and epsilon factors, we can define the gamma factors. Okay, and because this is also depending on the psi. So the epsilon factor is depending on the psi. Let me just probably add the psi here, the additive character. So we also have psi here. Okay, so this is the local gamma factor. Okay, and from the functional equation properties for the epsilon factor, we also have the functional equations for the gamma factors. The L function will be cancelled. So, which means if you take the you multiply with the gamma factor of its country gradients, you can also get 1. So this is the functional equation for the gamma factor. Okay, now, so after we have these definitions, now let's apply this definition to our previous examples. We already see for the Archimedean case, we already have the answers. And for the non-Archimedean case, for example, if we have the Weil representation is irreducible, let's say the dimension is greater than 1. Okay. And we know this is going to corresponding to this is the irreducible admissible representation of the V group. This is for the Archimedean case, for the non-Archimedean case. Okay. And we know this is corresponding to the essential supercuspidal representations for the GRN. And in this case, you don't have the initial invariant subgroup. I mean, for the SL2 part, the restriction, for the SL2 part, the image is trivial. That's going to give you a L parameters for the GLN. And this is corresponding to the supercuspidal representation. And we have the L factor in this case is just trivial. But the epsilon factor is going to be extremely complicated. And if you use the inductive to degree 0 formulas, you can actually compute the dimensional 2 case, the examples I gave. Okay, the second case is another extreme case, which is the unramified representation, the spherical representation. And we have, let's see, the irreducible unramified representation of the GLN. This is corresponding to the unramified L parameters of the GL case. And for the unramified side, we know the unramified L parameter is the parameter such that the phi restricted to the SL2 is trivial, and also the phi restricted to the initial is trivial. So essentially, the image is only determined by, the L parameter is determined by the image of the Frobenius element. So in that case, this is going to give us a semi-simple conjugacy class instead of the GLNC. And on the other side, we have the unramified representation is coming from the induced representation from the Borel, and with the unramified characters. And in this case, the image of the Frobenius element is going to give us by this character, unramified characters. So this is our correspondence. And if we apply our definition, because the restricted to SL2 is 0, is trivial, and also every vector is the initial invariant, we have the L factor is just the product over I from 1 goes to n. Okay. And in this case, the epsilon factor is extremely simple. It's just trivial. And of course, we normalize the Howard errors and also the additive characters. So this is the recipes and the examples for the local L factors. And now come to the exercise. So I have two simple exercises. The first is over the Archimedean case, you can pick up your favorite group and also your favorite representations over the complex deal groups. Okay. So I will take the connected split reductive group, and you can check for the classical group. You can see the tables in VTEX talk, and also you can pick up a representations for this dual group. And now the question is, we know how to write down explicitly write down the L factors. You can consider all the possible representations. So we can write down the L factors for these representations. Let's see. And we know this, we expect this is going to be a product of the gamma functions, the Euro gamma function. So now the question is, what is the location of the pause? I mean, for example, what is the largest possible location? What is the location of the pause in the right half plane? And what is the largest one you can have? And yeah, and this location is only determined by your data for phi, the sequence of the pairs, the pair of the integers and the complex numbers, and also determined by the Hash weight of the row. If you take the row, it's irreducible. So it's only determined by these two, the two invariants. Let's see. Okay. And also the interesting thing is if you have a product of such gamma functions, if you forget this representation theory, and now the question is, can you have any other interesting interpretations for the product of the gamma functions? So my question is, if we forget the representation, just look at this product of the gamma functions, and could you have any other interesting interpretations for this gamma function, like the hypergeometrical function or other? It's depending on, I mean, like an integral system. So it's depending on what is your background, and it could be interesting if you give the different meanings for this product of the gamma functions. Okay, so that is the first one. And for the second one, we take the F is a p-adic case. The first one is quite simple. Just apply the formulas and apply to calculated weights. You can easily to write down the pause. And the second one is I give a complete list for the irreducible, two-dimensional irreducible wave representations. And now, so and in this case, we know the L function will be just trivial, but I'm going to change the rho. Okay. I'm going to change the rho to the symmetrical nth power. And in this case, it's, in general, it's no longer trivial representations. You could have a pause. So the question is, can you pick up this, those representations? And also, for the epsilon factor, even for this two-dimensional representation, the epsilon factor, if you take the n is equal to 1, the epsilon factor is still very hard to compute. But if you change the n to be bigger, say, if you take the n is bigger, it turns out this is not that bad. And you can actually write down these epsilon factors in terms of the epsilon factors of the GL1, the character case. Okay. And if you have all of this, you can write down the gamma functions for all the symmetrical nth powers of the GL2, a local one. So I will leave this as an exercise, and in the next few talks, we probably will revisit those examples again, I mean the local version. Okay, so I will stop here for today's talk.